Greetings and welcome to a new video. In this video we will discuss the frequency response of a BJT amplifier, and we will specifically look at the emitter follower circuit, and we will use the short circuit time constant method to discuss the lower cutoff frequency estimation and also discuss how we can determine the maximum voltage gain for this circuit. Of course, we will see everything step by step in our calculations and verify this in SPICE simulations. Okay, we have the following circuit. You see here the emitter follower where we have the input through this resistor and the AC coupled C1 capacitor, and we measure also again AC coupled through the capacitor C2 at the emitter node. We have the resistors here and also the capacitor values are all shown here, so this is given. We have the BJT Q1 here. It has the following specifications. The base emitter voltage is 700 millivolts. The beta for this BJT is 290, and we have the early voltage which is 100 volts. So that is also another effect of this transistor we will discuss in more detail in this example. We would like to determine the following: maximum voltage gain and the lower cutoff frequency for this circuit. So let's see how we can work out the solutions for this example. We start first with our DC analysis. That means we disconnect the capacitor because these are open for DC, so we will lose this part. You also lose the load, RL, so we actually get this mid part here, and then we assume also that we have the linear region operation for this transistor Q1. That means the collector current is beta times the base current. This is actually not 100% correct because we have also this early voltage effect, but it is really a minor error, so we can just leave this and continue with that formula. So this is now the circuit for the DC analysis. So you see again the capacitors are opened. That means you only have this part. In order to now continue, we can now apply here the Thevenin equivalent circuit at node B. That's actually what we see here. So we convert this into this one. So you see the B here again, the Thevenin resistance and the Thevenin voltage we need to determine. And then we can continue with the next steps. So Thevenin resistance is actually looking at node B back, and then also VCC we assume then it is shorter. That is how that works. Then we take then the R1 and R2 in parallel because that's effectively going to ground. So we have actually this resistor which is then in effect exactly 15 kilo ohm. So 40 kilo ohm and 24 kilo ohm in parallel will produce 15 kilo ohm. Okay, the Thevenin voltage is at this node just the voltage divider. So that's actually R2 over R1 plus R2 times the VCC, and that will result in 6.75 volts. Okay, now we have here 6.75 volts, 15 kilo ohm, and this is 0.7 volt or 700 millivolts, and this is the resistor we know, this is 500 ohms. So we can now apply here in this input, we can apply now here Kirchhoff's voltage law, so KVL at the input loop. We can say Thevenin voltage is equal to Thevenin resistance times the IB, which is the base current, plus the VBE, plus the voltage across RE. Now, we know what the emitter current is, beta plus 1 times the base current. So that is also given here. We can now substitute that in this expression. So we get now an expression where you see the base current as only unknown here. Now we can group these base currents together. You can see that. So the Thevenin resistance and the RE times the beta plus 1 together. And now subtract the VBE from the right side. You actually have this nice expression where you see the base current expression in terms of the other parameters in the resistors. Okay, let's bring it here and use that for the next steps. Now we can calculate the base current. So we know the Thevenin voltage, we know the Thevenin resistance and 500 ohms. So we can continue, and that will be then 37.69 microamps. And the collector current is just beta times the base current. So we know the beta. That will result in 10.93 milliamps, and the emitter current is just beta plus 1 times the base current, and that will result here in 291 times this base current. That will result in 10.97 milliamps, so almost 11 milliamps here. Okay, let's also check the condition for the assumption we have actually made, a linear region. So we first start with the Kirchhoff's voltage law at the output loop. So I start here at node, actually looking at this circuit, and then go all the way to ground. So I will develop actually VCC is equal to VCE plus this voltage across RE. That's actually shown here. So I would like to see how much this voltage across the collector emitter node is. And that is actually shown here, so we can say VCC minus the RE times IE, and we know this. So just 18 minus 500 times the 0.01097, and that will result in 12.52 volts, which is much larger than the minimum required 0.2 for the VCE. We can also do it in an alternative way. You can say, let's look at the voltage at node C and also at node B, because the node voltage C must be larger than node voltage B in order to say that this is working in a linear region. The collector voltage is just actually VCC, so you can actually see that this is directly 18 volts, so that is simple. How about VB? Now VB is the VBE plus the voltage across the RE. That's actually shown here, just again Kirchhoff's voltage law, and that will result in 6.185 volts, which is, as you see, VC is larger than a VB, so we can say BJT is indeed operating in the linear region or an active region, so our assumption was correct. Alright, let's continue and do now the AC analysis for our maximum voltage gain. That's the first step. You see here the model of our BJT. You see the R pi going from the base node. This beta times IB is our current controlled current source, because this current will be multiplied by beta, will be then flowing here. We also have the RO, which is our output intrinsic resistance or impedance, which is between the collector and the emitter. That is because the early voltage. If this was infinite, then we also have an open circuit here. What we also see here is that the C1 and C2 are perfectly shorted. That's why you see here the RE and RL effectively parallel. And you also see here the RI, which is also, again, here you see the R1 and R2 in parallel. Why? Because VCC is effectively shorted in the AC domain. So we see actually here at the collector node also short and ground. And this one, R1, is going to ground there, or effectively in parallel with R2. That's also what you see here. Alright, so we need to use this circuit to analyze the maximum voltage gain. Of course, first the formula and then determine the voltage gain itself. Let's bring up the parameters we need. We need the R pi, that is VT, which is thermal voltage over the DC base current. We have the DC base current. Thermal voltage is 26 millivolts, so we can calculate that it will be then 689.8 ohms. The RO, this one is approximate given by the early voltage divided by the DC collector current. So we have the DC collector current. We know it is 100 volts for the early voltage, and that will result in 9,148 ohms. All right, now there's a current here flowing actually through this resistor RO. I call it IO. And there is also a current here, which is exactly as IC, because this current is the actual IC, which is our collector current in the AC domain, which will split in two parts and then come back here again. And you see again here, IB plus IC will produce the emitter current IE. I will now apply for my analysis the Kirchhoff's current law, KCL, at the node emitter, so emitter node. That is then the emitter current is equal to the base current plus the collector current, as I said before. But the collector current itself is the beta times IB plus IO. That is shown here. And IO itself, if you look at it carefully, because that's VO, which is actually at this node, and the voltage across the RO is actually minus VO, looking at the direction of the current, because that's going from ground to this node, and we measure from this node to ground, so we measure opposite. You see here minus VO over RO. Now if I now take this together and then make an expression for the collector current, we see now here the beta times IB minus VO over RO. Now let's now substitute this part in here, and you see here IB plus beta times IB. So that is actually the expression where you normally see, but now we have the additional part because of this early voltage. So we have now this, and also additionally this part. Now we can continue now looking at the voltage at the output, which is VO. Well, the output voltage is the emitter current times the parallel combination of these two resistors, RE and RL. So this current will flow then actually through this combination effective resistance here. You can also say the following: the emitter current is actually what we see here. So let's take this and substitute that in here, which is actually shown here. I will now divide the left and right hand side by this parallel combination of the resistors, RE and RL. That's shown here. And I also bring this part, which is minus VO over RO, to the left side. Why? Because they are similar, which has this VO. So I have then this expression where you see the VO over this parallel combination of the resistors and plus the VO over RO. And what I see is I see actually 1 over the resistor combination plus another 1 over another resistor combination times the VO. This is actually shown here. And then again is equal to the beta plus 1 times the IB. And this is actually effectively the parallel combination of these 3 resistors in the denominator of this VO. So you can actually also write it down like so. So you can say VO divided by the parallel combination of these 3 resistors. That's effectively exact same expression as here. And now we see here the VO is equal to beta plus 1 times the parallel combination of these three resistors times IB. So we have an expression for our output voltage in terms of the resistors, beta and the base current. And how about the base voltage? Well, the base voltage is this node, so VB, that is the voltage across R pi, plus actually the voltage VO. And VO is actually shown here, so we can actually take this. Now we see here again an expression where you see the R pi, betas, and also in terms of just IB, which is our base current AC. Alright, now the voltage gain we can write down in more convenient way because we need to go all the way from the input VI to the output, and we can do it in 2 parts. We can say V over VI is actually VB over VI, so actually going from here to this node, and then from that node to that node. That's actually shown here, so VB over VI, that's the first part. And then from that node to the output, which is then this part. So I have already this, because that's just this one divided by that. We only need to do the VB over VI. Okay, let's then bring everything here together and then step by step determine these parts. So I said V over VB, that's here. So we have now the expression. This is just a voltage divider actually, effectively. And here I need to look at the base, which I call the ZEB, which is then the impedance looking at the base node. And also ZI, which I call now the looking into the input here, taking these 2 resistors also. So Z input base and Z input. So I will then have VB over VI, which is then Z input divided by RI plus Z input. That's actually what you see here. So ZIB is R pi plus the parallel combination of these 3 resistors times the beta plus 1. That's actually what you see here. Why? Because this current is only valid for R pi, but the current flowing through these 3 resistors effectively is beta times IB plus IB, so it is beta plus 1 times larger. That's actually what you see here. So it's actually magnified looking from base to emitter. So we can now first calculate these 3 resistors effectively. That's actually shown here. So this is then 1 over the 500 plus 1 over the 2000 plus 1 over the RO we have determined here. And then summation, and then that again 1 over the summation of that one is given by to the power minus 1. And that is then 383.2 ohms. So we know this. So we can calculate that. So just 209 times this one plus the R pi we have here, so that will result in 112.2 kilo ohms. And ZI, which is then this one, is the parallel combination of R1, R2 and the ZIB. That's shown here. Again, similar form, 1 over R1 plus 1 over R2 plus 1 over ZIB. That's what we see here. I mean here. And then again, 1 over that summation, and that will result in 13.23 kilo ohms. So effectively, I see from this node to ground 13.23 kilo ohms. But I see from this node to ground, so not taking this into account, I see this 112.2 kilo ohms. So I have actually this one. So that's the first part we actually had, and this is now ZI over RI plus ZI. That's this ZI and the RI from this example. So taking now all the values we have determined also from this example, we can now calculate what the voltage gain must be. That will be then 0.9864, which is an attenuation. It is almost 1, but still not a gain. And that will result in the dBs as minus 0.1189 dBs. Okay. Now, next one is about the lower cutoff frequency. For that, we need to bring up our small signal circuit for frequency analysis. That means the capacitors C1 and C2 will then come back in the picture. Now, we need to discuss here that using the short circuit time constant method. And effectively, that means consider the effect of one capacitor at a time, like in the superposition. So what we do is we look at the contribution of C1 and calculate then that complete contribution, and then do the same process for the C2 and then look at the results and then decide which one will be dominating. That will be then discussed shortly in detail and determine the lower cutoff frequency. So we start first with the contribution of by C1, and for all the analysis we disable all the independent sources. In this case we have only one, and we also short the other capacitors or disable all the capacitors. That means you have actually like that. So you look actually between these two nodes of the C1, you short your input, and you also short your C2 because that's what you need to disable. So what we need to do is determine the impedance seen by this capacitor C1. And that is the time constant then, what we determine associated with this capacitor C1. So how do we do that? Well, we determine this capacitor and the impedance associated with that one with a product, which will then be a time constant. So this one, C1, is the thing we need to determine. That is the impedance. Okay, so we look first here into the Zi, so into this node that is again as the same Zi as we have done it before, and that is what we first need to determine. And the series combination of this Zi and the Ri, that will be the impedance seen between these two nodes by this capacitor C1. And what about the Zi? Now we know the Zi and the ZIB just about the discussion we have did before. So Zi is the parallel combination of the R1 and R2 and the ZIB, and ZIB is what we have determined, which is this 112.2 kilo ohms. And Zi is then calculated using actually again the parallel combination of these three resistors, and that was already calculated in the discussion of the voltage gain. So we have now here 13.23 kilo ohms plus 100, and that together times 10 to the power minus 6, because that's 1 microfarad, that's shown here, and that will result in this 13.33 milliseconds approximately. And the pole frequency associated with this capacitor C1 is given by 1 over this time constant, which is then this, and that will result in 75.01 radians per second. Okay, now we need to go to the contribution by the C2, which is the capacitor here, and disable again the independent sources, and we also disable other capacitors. In this case we only short the C1, and so we look at the nodes of C2 and determine the impedance seen by the C2. And that time constant is again similar to the C1, is the product of the capacitor C2 and the impedance seen by this capacitor C2, which is the Z sub C2. So what do we see in this case? Now let's look at it in more detail. Now it's actually this RL, and then parallel actually to this resistor, and there is a ZIE, which is actually this one. So looking at the emitter up, you actually see a new impedance which is formed by these four resistors. So what is the ZIE, which is then impedance looking into the emitter? That's actually what I say here. Okay, let's do that first. Now we see here the R pi, and in series with the parallel combination of these three resistors, that's actually shown here, and then divided by beta plus 1. Why? Because we look from the emitter into the base, and that is then beta plus 1 times smaller. Like we have said, from the base of the emitter it was then beta plus 1 times larger, so it's kind of a magnification. So this is the impedance looking up here to the left side. That's this one, which is then almost 2.7 ohms, so very small. And that will be then in parallel with this RO, we already know, and also this RE, which is also what we have from this example. And that together will be then in series with our load resistor RL, which is 2 kilo ohms. So that's actually shown here. So 2000 plus the parallel combination of these three resistors, and that together times again 1 microfarad, so 10 to the power minus 6, and that will result in almost 2 milliseconds, so 2.003 milliseconds. Again, the pole frequency associated with this capacitor C2 is then given by 1 over this time constant, And that is then almost 500 radians per second, so more precisely 499.3 radians per second. Okay, now we have all of them, the contribution by C1 and C2. So let's bring them up here, and also other values. So in summary, we have these. How do we now proceed in order to determine or give a good estimation of this lower cutoff frequency? So we see here two pole frequencies. One of them is almost at 500 radians, and the other one is 75 radians per second. Now this one is at least 6 times, maybe approximately 6.7 times larger than that one. So we can approximate this as this is the dominant pole. So we have a dominant pole, we can say that, since this is at least 5 times larger than that one. So rule of thumb. And then we assume that our lower cutoff frequency is determined by this capacitor C2. So we can say the lower cutoff frequency is then omega L is approximately omega C2, which is then almost 499.3 radians per second. Now converting that to the hertz, just divided by 2 pi, will be almost 79.5 hertz, so maybe rounding off to 80 hertz, depending on, of course, the accuracy in our calculations. So this is the result using the dominant pole approximation. Okay, let's see now that in the simulation results. First, we start with the DC analysis. This is the circuit for DC analysis. You see some notes. And this is the table. And these were the results in the DC analysis calculations. So we see here, so I will just highlight some labels here. This is the resistor RE current, that one. And that was 11.075 milliamps, so almost 11.1 milliamps. And I see here almost 11 milliamps, so close to what we have calculated, so this is nice. You also see here the voltage at node 1, which is 6.24, let's say, volts. I see here 6.19 volts, so also very close, so you can say this is in good agreement. You also see at node 2, which is exactly 18 volts, of course, because that's just connected to the power supply VCC. All right, let's now look at one of the important results from the simulation, which is the Bode plot, where you see the gain and the lower cutoff frequency. So this is the circuit, and the gain we have determined in the calculation was 0.9864, and we have here minus 0. In dBs, of course, minus 0.1189 dBs, and we have here minus 0.1176 dBs. So it's very close, so we can say this is a perfect result. The lower cutoff frequency was determined as using the dominant pole approximation as 79.5 Hertz, and we see here 81.4 Hertz. Also actually very close to the agreement we have here, and also the BJT we have used in our simulation was the model of the BC547B, so there are many other parameters in this model, so we haven't taken into account. So I can say, using just this as the parameters for our BJT, still we have a very good result, so we can say this is all nice and checked. Alright, that was our example concerning the frequency response of this emitter follower BJT amplifier. If you have any questions, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.